The biggest shift this week is that AI is moving from predict what happens next to models that can actually reason about physical world state, from deformable objects to robot action. That matters because once you can ground vision in contact, geometry, and latent foresight, you stop guessing from pixels and start building systems that plan and act more reliably in the real world. What connects these results is a clear trend towards scalable simulation and embodied foundation models. Here's where the trade-offs finally show up and which approach seems to win when data, dynamics, and generalization all collide. Let's explore the first paper, Deform 360, a massive multi-view visual-octile dataset for deformable world models. Deform 360 is a large-scale visual-tactile benchmark for deformable world models, built by Brown University, Columbia University, and MIT to study whether 2D video generators or explicit 3D particle models better capture real manipulation physics. The dataset contains 198 daily life objects, 1,980 interaction sequences, 41 synchronized surround view cameras, and tactile grippers, totaling 23.3 million frames and 215.7 hours of recordings. Its markerless annotation pipeline combines per-frame 3D Gaussian splatting, multi-view 2D, point tracking with CoTracker 3, 3D back projection, ransack fusion, and tactile regularization to recover dense particle trajectories under heavy occlusion. On reconstruction, the pipeline reaches 27.66 decibels, PSNR overall, and tactile refinement reduces warped point cloud chamfer error from 1.41 times 10 to the power of -4 square meters to 2.71 times 10 to the power of -5 square meters, a 5-fold improvement. For contact prediction, a transformer model achieves 88.67% accuracy and 0.8909 F1 across 36 synchronized views. In world model benchmarking, PhysTwin is strongest in low data per episode settings, while Cosmos Predict 2.52b, an NVIDIA Foundation video model, generalizes better in zero-shot multi-object prediction, revealing a concrete trade-off between structural priors and scaling. Let's explore the second paper. Image 2 Sim Scaling Embodied Navigation via Generative Neural Simulator. Image 2 Sim from National University of Singapore and HKUST reframes embodied navigation as a scaling problem in neural simulation rather than manual annotation. The paper's core idea is to decouple persistent 3D grounding from photorealistic rendering. A feed-forward feature Gaussian encoder lifts posed RGBD captures into explicit geometry and semantics in one pass. Then a geometry-aware one-step pixel flow renderer completes missing regions with a conditional mean flow model guided by alpha maps and DNOF 3 features. This produces a real-time simulator that renders panoramic RGBD at about 40 frames per second on a single RTX 4090, while also serving as an automatic embodied data engine. Using RealC 3D, Structure 3D, ARKit scenes, HM3D, Scanet, Gibson, and Matterport 3D, it constructs 19,936 interactive scenes and synthesizes over 10 M-Vision language action samples. Training Image 2 Nav only in Image 2, SIM yields new state-of-the-art zero-shot transfer in Habitat, including 70.3 steradians and 65.6 SPL on R2R CE with 180 degrees FOV, 70.7 steradians and 59.1 SPL on RXRCE, and 53.7 steradians and 42.7 SPL on RevRec. The scaling study shows consistent gains from 46.1 to 66.3 steradians as synthetic training grows from the human annotated baseline to 10 M samples, and real-world tests on a Hello Robot Stretch 3 improved path following success from 8/20 to 11/20, and goal-oriented success from 5/20 to 9/20, indicating that physically executable neural simulation can narrow the sim-to-real gap for embodied navigation. Let's explore the third paper, Intern VLA A1, 5, Unifying Understanding, Latent Foresight, and Action for Compositional Generalization. Intern VLA A1, 5 from the Physical Intelligence team at Shanghai AI Laboratory unifies vision language understanding, latent foresight, and continuous action for robot manipulation by building on a native Qwen 3.5.2b VLM backbone and adding a lightweight 460M unified expert Instead of learning future frames directly in pixel space, it turns prediction into a latent querying problem with 50 learnable foresight tokens that are supervised through a frozen WAN 2.25b video generator, so the policy inherits dynamics priors without paying inference time generation cost. The model is pre-trained on 1, 2 M robot episodes and about 3 M multimodal samples, with stage 1 and stage 2 training runs of 300K and 600K steps. And it uses a single next token objective for VQA, subtask prediction, and discrete action tokens before switching to flow matching for continuous action chunks. Across 6 simulation benchmarks, it reaches 98.9 on Libero, 84.8 on Libero Plus, 93.2 on RoboTwin 2, 49.5 on eBench, and 80,8 on simpler ENV, while in real-world tests, it posts 75.9 on sort tubes, 80.5 on insert tubes, 76.4 on move tubes, and 76.4 on the 13-step MOF procedure, clearly outperforming Pi 0.5 and Modus on the hardest compositional and long horizon settings. That's a wrap on today's AI paper highlights. Thanks for watching.